The left turning tendency is strongest at low airspeeds, such as during takeoff roll, after the pitch-up rotation, and during steep initial climbs at low airspeeds, such as Vx and Vy. As the angle of attack is reduced, less and less rudder force is required to counteract the left turning tendency. The propeller slipstream exists throughout the speed envelope and creates a nose left turning tendency, which is pronounced at low airspeeds and decreases proportionally with increases in speed. Torque influences roll about the longitudinal axis, a counterclockwise rotation of the fuselage when viewed from the cockpit. It is also predominant at low airspeeds. Respecting rotation speed and minimum approach speed provides control authority against the effects of torque. Aggressive pitch-up transitions, as in a rapid rotation at takeoff, creates a nose-right turning tendency, gyroscopic precession. The same is true with aggressive pitch-down transitions, as with a brisk stall recovery. But the turning tendency would be to the left. The effect is also more pronounced at low airspeeds. Understanding the flight control inputs required to counteract the left yawing tendencies created by P-factor and slipstream is straightforward. Right rudder force is required. Gyroscopic precession, another yawing tendency, is apparent during pitch changes, thus it is momentary. Brief right or left rudder force is required. Torque, which is most obvious with an abrupt increase in power, is different. Torque induces roll and is strongest when flying slowly, when the weather-vaning properties of an airplane are at a minimum. Earlier we mentioned that the primary flight controls used to roll an airplane were the ailerons, which is true. Unfortunately, ailerons have two byproducts which are undesirable when flying at minimum controllable airspeed. Ailerons increase angle of attack, and they produce adverse yaw. On all airplanes, the lifting aileron increases the angle of attack at the associated outboard wing section. Lift is manipulated to roll an airplane. Therefore, if one is truly flying at minimum controllable airspeed, any increase in the wing's angle of attack would exceed the critical angle of attack, resulting in a wing stall. Moreover, if the critical angle of attack is exceeded by the lifting aileron, a stall results and the airplane rolls in the direction of the stall. Applying more aileron worsens the situation. Regarding adverse yaw, when increasing lift, an aileron also induces drag, which pulls or drags the nose of the airplane in the opposite direction to the roll. In this example, if one wanted to roll to the right, to wings level, the nose would yaw to the left, against the desired direction of movement. This is also an undesired effect when maintaining coordinated flight at minimum controllable airspeed. The TBM's advanced aerodynamic design incorporates spoilerons, which assist with roll control and mitigate adverse yaw. Despite this aerodynamic advantage, one should manage propellers' rolling and yawing tendencies by giving the rudder priority for roll control when maneuvering in the low-speed regime.